All right, here are the notes for Properties of Water, section 2.2 in your textbook. So the first concept is talking about how important water is to life on Earth. Actually, if you've been following the news, you might have heard that they just discovered flowing water on Mars. This is a big discovery, can give us clues into other planets, possibly other solar systems, if life can develop in those waters. But anyways, that was a little bit of a tangent. Water's properties can help us answer questions like, how can water get from the roots of trees up to the very top? Why does ice float? How is it that insects can walk on water? And if we dehydrate, that is a serious, serious problem. Why would we die without that? All of those things previously discussed can be explained by the unique structure of water. So water, we know, is H2O. So there is two hydrogens, one there and one here, to one oxygen atom. And they form covalent bonds. And the covalent bonds, remember, is electron sharing. We just talked about that. So this molecule also is what's called a polar molecule. Polarity has to do with the uneven distribution of those electrons, which we also discussed yesterday, around the elements. So oxygen has, I think it has 8 electrons. It is what's called electronegative, okay? Hydrogen, on the other hand, only has 1 electron. So in comparison to oxygen, it is positively charged. When you have the distribution or the uneven distribution of charges, oxygen is much more negative and hydrogens are more positive. That is called polar. So water is a polar molecule. So this slide has the words to what I just explained, basically. Electrons in a polar molecule are unevenly distributed, creates regions with slight charges. The oxygen, again, is negatively charged. The hydrogen is slightly positively charged. I like to use this diagram to help my students remember that water is polar. I think of the water molecule as being, this is our oxygen, these are our 2 hydrogens, and I think of a polar bear's head. This is our polar bear. You can't see it. I'll show you the slide tomorrow when I can actually like flip through it, and then you can see the polar bear's head. But here is the positive, that is on the ears, and the mouth of the polar bear, that is the negative oxygen. And there would be, oops, the eyes right there and right there. That looks like he has a tooth that's missing. And that's the nose. That's a cute polar bear. All right, and this brings us to the structure of water and how it interacts with neighboring water molecules. The hydrogen bonds are the last type of, or another type of bond that we can talk about in biology. We already talked about covalent bonds. Those are our strongest bonds. Then we have ionic bonds. Now we have hydrogen bonds. Hydrogen bonds form between water molecules. So the bonding within this water molecule, remember, is covalent. All right? But between this water molecule and this water molecule, we have hydrogen bonding. That means that there is an attraction between the slightly positively charged end of this hydrogen and the slightly negatively charged end of that oxygen. So again, it's those attraction between the positive and the negative that form this bond. Now, when we think about the strength of this bond, it is not very strong. If you think about water, water flows, okay? So when water is flowing on your hands, when you're washing them under the sink, those bonds are breaking and reforming super duper duper fast, and water flows. Now, when would those bonds stay static and not move? That's when water would be in the frozen form and you have ice. Those ice crystals form, those hydrogen bonds stop moving, and they are solid. So we're just going to run through quick some of the properties related to hydrogen bonds. Water has a high specific heat, so water is going to resist changes in temperature. That's why it takes a while for water to boil. That's also why in the wintertime, air temperature gets really cold, but a lot of times it takes a while for ponds, lakes to freeze over because water retains that heat. That's also why on coastal regions, if you think of California, even the East Coast, we have those big, huge oceans and bodies of water. They help to regulate air temperature. So usually you have a much more, what's the word I'm looking for? Why can't I think of it? Not extreme climate, the opposite of not extreme climate on the coasts. All right, cohesion is another property related to hydrogen bonds. This is water molecules sticking to each other. So they are going to form water droplets. They also produce surface tension, which is why some small bugs can walk on water. Part of the lab is going to be looking at water droplets sticking to each other. Okay, so that's why water does form these nice droplets. It sticks to each other. Water also sticks to other things. So if you think about your windshield or your window when it's raining, the water droplets hit and they come down the window. Okay, so water not only sticks to itself, but it also sticks to other things, and it's good that it can stick to other things because that's why plants are able to bring water up from the roots to their leaves. That's part of the process because it sticks to the inside of those cell walls. Water is also referred to as the universal solvent. So solutions form when one substance dissolves in another. The top of page 40 talks about solutions and solvents and solutes. The solvent is the substance that is present in the greater amount and that dissolves the other substance. So the solvent, in this case, water is a universal solvent. What is dissolving in it are going to be the particles, let's say like salt. Those then would be referred to as the solute. And here we go. Here's a diagram of what I just talked about. A better diagram than my little scratches. We have the solvent that is doing the dissolving, and the solute is the particle that is being dissolved. Roxy just trotted in here. You could see her, or you could hear her little caller. Roxy, want to give a shout out to my classes? She's being shy. All right, the last thing that's being covered in this section is pH, the pH scale. I'm sure you've heard about. You know that things are acidic and things are basic. What it's measuring is the concentration of hydrogen ions in a solution. The scale goes from 0, way down at this end, to 14, which is way up here. And then we have neutral, which is right smack dab in the middle, and that is going to be either acidic or basic. And what this actually means is that if a compound is an acid, it is going to be releasing hydrogen ions when it dissolves in water. So as you go from slightly acidic to very, 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 very acidic, you have more and more and more of those hydrogen ions in concentration. And usually these things are going to be very sour tasting, like coffee and, no, not coffee, orange juice, anything acidic. Pop, Coke are going to be acidic, so they are releasing H+ when dissolved in water. On the other end of the spectrum is our bases. These are going to remove H+ from a solution when they're dissolved in water. They have a relatively low concentration of H+ ions in solution. They are going to be increasing on the basic side, going up to 14, and these are going to be usually bitter tasting things like coffee and a lot of cleaning supplies. Not that you'd be drinking cleaning supplies, you shouldn't be drinking cleaning supplies. These are going to be also very basic. All right, that wraps up the screencast for the 2.2 notes. I'll be stamping those tomorrow and asking what you need more clarification on. We'll go through polarity again and hydrogen bonds for sure. And then we're going to be doing some activities in the lab to showcase or show some of these properties of water.